Hello, good morning. This is Pavan Turaga from Arizona State University. And today I'll be talking about geometric methods and movement analysis for health and rehab. This is for the mini symposium being organized by Sebastian Kurtik and team for the SIAM Mathematics of Data Science 2020 conference. Thank you so much for the invitation. I have about 25 minutes to speak, and I'll try my best to end on time. And I will be talking about a few topics which we have been pursuing over the past few years in representing time series measured from human activity from a variety of sensors, including wearable devices, including depth sensors, motion capture devices, in a way that helps in understanding some intricate properties of the human movement, especially as applied for healthcare applications, including physical rehabilitation, and general measurement of activity for several interventions in healthcare. So even though many of the techniques that we will talk about are fairly general purpose as they apply to time series, I will try and make the case for most of the things that we have been doing in the context of wearables. Wearables is, it refers to a variety of sensing mechanisms, including discrete, visible units like a Fitbit, an Apple Watch, or things that are a little more spread around the body, like a wearable network of sensors like IMUs that people use in clinics for balance and gait measures. The reason why we're interested in wearables is that it's a growing market. Here are some statistics. These are statistics of Fitbit use over the past decade or so. And you can see that the growth is actually pretty dramatic. And if you include other kinds of wearables beyond the Fitbit, the growth is poised to explode over the next decade. Practitioners in healthcare are increasingly interested in the implications of wearable technology for health tracking and biomarker estimation, and for prevention and treatment and rehabilitation of many diseases, including prediabetes, including neurological things which have to do with gait and balance, including estimation of biomarkers for non-invasive estimation of biomarkers like your blood pressure, glucose levels, HDLs. The spectrum of health applications impacted by wearables is just remarkable. This is just to provide you more context as to what's coming in this area. Today, when we speak of wearables, the common things we think of are Fitbits, Apple Watches, things that you can wear as an accessory and that's visible to people. The future is moving towards invisible wearables, which are maybe like a small bandage or band-aid, a patch that just sticks to your skin. It could be transparent. It could be a piece of flexible electronics which molds to the shape of your body, and it can just go anywhere you want it to go to. It could include a fabric that is embedded, that is made of special kinds of material, which creates interesting electrical signals when it is stretched and sheared. Or it could also include electronics that can be sewn into fabric. There are or even just written in interesting conductive ink. So there's all manner of things happening in wearables. And many of these things are also poised to be energy harvesting capable, meaning as you move or as you experience light falling on you, there is electronic devices which can recharge their batteries based off of physical movement, based off of incoming electromagnetic radiation. And all of that goes towards increasing the battery life of the wearable, so you keep wearing it for longer without needing to take it off for recharging, which means more longer data capture and more data coming. That's the future. We are headed that way in the next decade. It increases the complexity of representation challenges. It increases, it introduces new kinds of mathematical challenges, which we will touch upon here in a small way. The clinical questions of relevance that people are interested in, and we are working with a lot of clinical partners who use data sets like this. The spectrum is wide. I work with faculty Matthew Buman from the College of Health Solutions at Arizona State. They are interested in one level at simply labeling of human activity. They call this the measurement problem. What are you doing and how much of your time is spent doing one of 20 activities of interest? And that's just the beginning. Then there's other kinds of meta-analyses, which is your activity in the 24/7 spectrum over several months? Does it exhibit some kind of periodicity or quasi-periodicity? The existence of periodicities in human activity signifies good things about your health and your lifestyle. The lack of periodicity as measured by a wearable device can indicate decline in health, and it correlates with decline in biomarkers like HDL and blood pressure and stuff like that. It's very remarkable. And of course, there is also the grand goal where we are headed, and we would very much like to be at the forefront of that, which is prediction of biomarkers. Now, biomarkers can mean a variety of things. The simple ones are the measures that you get from blood work, your blood glucose levels, lipid profiles, all that is a valid biomarker, to behavioral biomarkers, which can range from gait and balance measures to cognitive decline and mental decline. All of that is being considered under this paradigm of wearable tech. We are scratching the surface in the algorithmic side on these problems, and let's get to some examples. So when we started working with accelerometers, we started working on this about 3 or 4 years ago. The first thing we realized is you might think of data from an accelerometer as simply a time series, but it has interesting features and it has interesting dependencies on where you place it, how you place it, that makes analysis a little difficult. First of all, one of the most common sensors in a wearable device is accelerometer, which measures acceleration along three perpendicular directions, X, Y, and Z, which is the coordinates are intrinsic to the sensor. So the way you attach the sensor to your body changes the coordinate frame. And to make it physically meaningful and physically consistent to the same coordinate frame in some other reference frame is a very, very non-trivial problem. Most accelerometers will also record a constant G component, the natural gravity of the Earth, but it's not always going to be aligned with the Z axis of the sensor. It will have some components along all three axes of the sensor because the sensor is misaligned. It's not always aligned with what you would consider the vertical. So there is always this constant G, which just messes things up. Removing that G requires other kinds of sensors like magnetometers and gyros and sensor fusion. It's not very easy to deal with these sorts of nuisance parameters. And then the sampling rates are fairly high. Sampling rates for accelerometers nowadays are upwards of 100 hertz. 100 hertz would be considered very basic. So representing data for 24/7, the raw data points easily run into the millions, and then processing them and getting some interesting information is a difficult computational challenge. One of the first entry points we had into the space is through the lens of understanding sources of variation and variability. It is very well understood in human activity modeling that the same action performed by the same person at a different time of day will give rise to slightly different signal recordings from an accelerometer or even from motion capture. And this is very similar to findings 2 or 3 decades ago in the field of speech analysis, where people found that the same person saying the same syllable or the same vowel at a different time of day gives rise to slightly different recordings as measured by your microphone. It's just the intrinsic variability of human speech in that case, and human movement in our case. Human movement is not perfectly repeatable. You cannot walk the exact same way if I made you walk 10 times. And when you're sampling such a variable signal at high sampling rates, 100 hertz and beyond, that variability is brought into sharp relief. You cannot avoid it. If it were a low-grade sensor not sampling at such high levels of fidelity, maybe that variability gets quantized out, but in good grade, good sensors, that variability has to be contented with. What is the nature of that variability? The next question. Here are some standard factors of variability that the community is trying to understand. The first one is intrinsic variability of human movement, which I'm terming it as phasing variability. So phasing in gait is a well-known phenomena, which is when you're walking or if you're doing an action, certain phases of your movement can be done faster and certain can be done slower. And it does happen that when you repeat the same movement 10 times, your phasing changes a little bit. Mathematically speaking, that phase variability can be modeled through techniques like time warping. And that's the goal of this talk, to look at how can you use time warping methods and time unwarping methods to reduce that variability. There are other interesting kinds of variabilities. Sensors themselves have internal shifts in their operating points. A sensor doesn't always sample at exactly the same sampling rate. There is some drift all the time. And depending upon the temperature, the ambient temperature, it can introduce some noise. The clock can go off a little bit based off of electromagnetic interference. So there's interesting kinds of effects that the sensor undergoes, which affects data. We don't have very good models for all those sources of variability, but for some we do. Placement variability is another interesting thing. If you wear an Apple Watch or a Fitbit, there is no guarantee that you're wearing it at exactly the same location all the time. You're wearing it in approximately the same location, but not the same. And that introduces a different kind of variability. And sometimes it helps to view that phenomena through the lens of nonlinear dynamics. And we have a separate body of work which tries to look at that source of variability, which I'm not going to talk about here. In brief, the idea is, if you think of human movement as a complex nonlinear dynamical system from which you're taking low-dimensional observations through this wearable device, and misplacements imply you're taking slightly different projections of the dynamical system, then through methods like Tackins's embedding theorem, you can reconstruct some topologically equivalent surrogates of the dynamics, and the variability due to sensor placement reflects as a deformation of the reconstructed phase space, for which you need some topologically invariant features to be derived. Slightly different body of work. The fourth source of variability is the hardest, demographic variability. Body types, they affect data. Your weight affects data. Your gender affects data. Body height and shape, all these things affect the recorded data in ways that is not fully understood. So all of these sources of variability exist in sensor data that's recorded, and we are trying to find ways to reduce the variability, or at least understand it, factor it out through some geometric methods. The first one that we'll talk about in a little detail today is this idea of phase variability. As I mentioned earlier, human movement, when done several times by the same person under the same conditions, still exhibits phasing variability. Some parts of the movement are faster than others, some parts are slower than others. So when you see the time series, there is time warping effects observed in the data. The formal way to think about it, there's a few in the old 80s ways of thinking. You would consider techniques like dynamic time warping, which would take a signal and find an optimal alignment given a template. We are looking at methods that have been developed by folks in FSU, Florida State University, Anuj Srivastava and their team, called square root velocity functions, which address some of the issues in DTW methods. Specifically, DTW can suffer from pinching effects. It can make some very unusual warps happen unless you constrain it. And it also doesn't, it allows you to compute a measure of divergence between two time series, but it doesn't quite allow us to compute statistical quantities like an average signal. and standard deviation envelopes, things like that. I will not have time to go into a tutorial on SRVF. There's a lot of material written by Anuj Srivastava and Eric Klassen and even Sebastian Kurtek. They've all written tomes on this topic. The high-level idea is, given a stack of signals, the SRVF methodology will allow us to solve for a template, a mean signal, and also find standard deviation envelopes from that stack, which basically tells you that, and there is a distribution over warp functions that it can estimate, which explains the observed variability. In the old signal processing ways of thinking of things, they've called this the amplitude and phase separation, which is when you have this average signal, which has been estimated, factoring out temporal warps. And when you align the signals to the average signal, you get the amplitude function. And the time warp that aligns a given signal to this average signal is the phase function. So you are able to decouple sort of the shape, the invariant shape of the signal, and that shape altering nuisance parameters separately. It's there to be used if needed. This is how the process sort of looks like. A stack of data, which right here, which on first glance looks fairly chaotic and with no structure, can be decoupled into phase functions or warping functions and amplitude functions. Now, this is 100 recordings of a person walking at some constant speed on a treadmill, like 4 miles per hour. And when you just overlay them, there is this temporal misalignment problem, because when you also window signals, there is no guarantee that the peaks and valleys will be aligned. So there is misalignment introduced not only because of internal variabilities, but also because of this windowing operation in time. In the older days, you would simply take a signal like that, don't worry about the misalignment problem, and compute some simple summary features like the DCT in the window, or the Fourier transform, or some other simple energy kind of features, and plug it to a statistical classifier like an SVM for activity recognition. In this paper that we're citing at the bottom, what we showed was, if you used SRVF methods to estimate a template per class, and if you use those templates to factor out this time warp before any classification occurred, we find that classification performance improves, the variability of the computed features reduces, and in general, we see this trend across many different conditions and many different activity classes. So here is an example. So these are 7 different activities of interest we had, which came to us from our clinical partner, Matthew Bowman. And many of these are structured activities, like walking on a treadmill at very special speeds and at very special grades. And you can see that there's 2 kinds of walking, and maybe walking down the stairs. And they're all walking, they have the same kind of quasi-periodic structure repeating. And then there's some very different looking activities, like seated and stacking folding laundry, which don't necessarily have a periodic structure. So some activities are easily recognizable, but some others are not. So we went through a very classic activity classification pipeline, which is take these temporal windows of time, compute some simple energy kind of features, plug it to an SVM, and let the classification be done by the SVM. The only thing we changed was what the inputs were for the feature extraction component. Case 1 was pass it on as is, the raw data goes as is. Case 2 was you pre-align it with SRVF pre-processing, and then you pass these pre-aligned signals, and what happens then? The results were that, and what features we used, not very important. We found this is stable across features, but roughly some kind of energy kind of features and Fourier transform kind of features. Here are results of, so this table summarizes the improvements which observed in classification accuracy because of that pre-alignment step. High-level view, performance increases significantly across many different time series lengths. So it's consistent across time series lengths, but because of the pre-alignment step, we are a bit slower by an order of magnitude, but we have ways to consider speeding things up. And what are the classes where the maximum amount of improvement occurs. So this graphic shows us where the maximum improvements are happening. And we find that the maximum improvements are happening in classes 1, 2, and 7, which refer to walking treadmill at 1 mile per hour, walking treadmill at 4 miles per hour, and walking downstairs at 5 floors, a flight of 5 floors, which are all walking activities of slightly different kinds, and therefore naturally they are confusing amongst each other. But if you estimate these templates per class, then that variability is somehow the variability across classes is being preserved, and signals are getting a bit cleaner when you do this phase separation. So here are some confusion matrices for the same phenomena, and we can see that this is the baseline approach where there is no pre-alignment. The classification accuracies for class 1, 2, and 7 are relatively low, and they jump up. 77 becomes 91, 73 becomes 84, 69 becomes 79, and that helps bump up performance. And generally, everything improves a little bit. So this gave us interesting new directions to pursue, in the sense that we were earlier looking at alignment as a pre-processing step and using classic features that people have used for a long time, for a decade now, for activity classification. With the rise of deep learning, the natural question that we would like to address is, can you integrate the two? Can you create deep networks which learn features? Now it's been shown that learned features generally do better than features that are not learned or hand-tuned features. But doing feature learning with this idea that they want to be invariant to, let's say, time warping is not an easy problem. At best, the deep learning ways of thinking tell us that if you want to be invariant to this time warping, maybe do some kind of data augmentation, take a given time signal and warp it in many different ways, which means increase the training set really artificially, and hope that the deep network will eventually learn to factor out the nuisance parameter by itself. We wanted to find a technique which would leverage the known mathematics of how time warping works and see if we can constrain some layers in standard deep net architectures so that we don't have to necessarily create new networks, but use existing networks for activity classification, but maybe drop in certain modules for removing the effect of the nuisance parameters. So that was our design thinking, which is leverage existing architectures, don't necessarily go down the path of artificially increasing the training set with more variability, because that just slows things down. We don't know how much variability is needed to be introduced. It's a wasteful, ignorance of known knowledge. So how can we use known knowledge to better regularize and constrain our deep networks? So we came up with this idea of a temporal transformer net, which was motivated by certain techniques which have been used in computer vision for spatial alignment of images and shapes. The idea being that you introduce a module, in our case, a temporal transformer, which does something really simple. The whole module works and in the context of increasing classification accuracy. So this is special for classification problems. You're trying to make the deep net warp a given input signal in a way that maximizes the end goal of classification. There are some trainable layers, which of course you have some freedom to design how they look. We use some fully connected layers and some 1D convolutions. What we want these trainable layers to spit out is a warp function. And the way we force it to spit out a warp function is to introduce constraints in this layer that will, sort of using the square root velocities ways of thinking, which is a valid warp function. When you take its square root, will become a PDF. I mean, a derivative and a square root, right? You take a derivative and then a square root, it becomes a PDF, and then the square root makes it a point on a sphere. So you can introduce some of the spherical constraints and the dot, the derivative operation and the square root operation inside these constraint layers. And out comes some function You also enforce it to be, continuously increasing. And the way you also sort of force it to behave like a warp function is by actually introducing a warping module, which takes this function and warps the given input according to this function, and out comes a warp function. And this warp function goes into a classifier, and the classifier network spits out a label. So when you train this model end to end, this temporal transformer will learn to spit out actually useful warp functions, which maximize the end loss function, which is based off of classification accuracies. That's the way of thinking about it. And we found that it actually works interestingly well. Here is some synthetic data. This was a CVPR paper, and I'm already running out of time, which shows that you can train a neural net to separate out classes using these kinds of automatically estimated warp functions. When it comes to activity recognition, the capability it affords you is that you can drop in a module into existing classification networks. And we found that even in large-scale activity recognition pipelines like ICL action dataset, which have 45 classes based off of push and capture, we find that our numbers actually go up when you drop this in to standard classification networks like LST and METS. We have not yet integrated this pipeline into the data set we showed you a few slides earlier, which is an internal data set. It's not publicly available. And we are in the process of connecting the two dots. I mean, for CVPR, we had to use public data sets. CVPR doesn't encourage these kinds of private accelerometer-based data sets. So we were also trying to make these ideas appealing to certain communities. In this case, this was a CVPR paper. So we went on the idea of using it for motion capture data, not wearable data, but the same techniques apply. Now, what we just saw, the temporal transformer network solves an interesting problem of action classification, where temporal alignment becomes a drop-in module, but the goal is always to increase classification accuracy. So if you have to do other kinds of things like biomarker estimation or other things which are not necessarily classification problems, maybe there are regression problems. Now there are use cases in digital health where you want to take activity data, accelerometer data, and regress perhaps heart rate or energy expenditure or breath rate, things which are continuous valued, not classification labels. So what features should I use then? The TTN features could potentially be useful, but we wanted to investigate how could we create a standalone feature learner, sort of like an autoencoder that is not necessarily tuned for any special task like classification. It's just there as a representational approach. So how can we define an autoencoder which also learns to factor out this temporal variability bit if needed? So the idea here was to create an encoder net which reduces dimensions to a latent space. In a classic autoencoder, you would just take the latent space and put it into a decoder, and you would hope that the outcome of the decoder is close to the input. So you minimize the L2 loss between the input and the output. The difference we introduced was we want to learn these latent vectors such that rate variations have been factored out. To explicitly enforce the factoring out of the rate variations, we introduce a smaller component. So Z here is the latent code. V here is the vector which we hope will contain that phase function. Once again, the same logic. How do we enforce it to learn phase functions? Is we introduce certain constraint satisfaction layers, very much like the dot, the square root and the derivative operations, making sure things are positive. And we get a function that hopefully looks like a rate function, a phase function. And again, the way we force it to learn a phase function is you take the other part of the latent code, which hopefully has learned to factor out the phase function, dump it into a decoder, and then hopefully this is now rate invariant. So you have a rate invariant component and you have a phase function that comes out, compose the two together, convolve them, and what you should get is the input. So you're minimizing now the L2 error between the input and the reconstruction, where the reconstruction is arrived at by splitting your latent space into 2 bits. One bit acts like a feature, and the other bit acts like a phase function, and you can compose the two together with actual real function composition. It turns out that these are all trainable, these are all differentiable layers, so you can train them into it. Once again, some of our results are very surprising. We find that so this is an optimization problem which has no reason to converge to meaningful warps. It could converge to any warp, right? You have this group action ambiguity. You can take the warp functions and warp them all again, and it would still be a valid set of warps. And there is no reason why your warp functions should be close to the diagonal. So, but we're finding that even so, the deep nets, the autoencoders are learning some commonsensical warp functions. We don't necessarily have a result to explain why, but it's empirically true so far that they learn these meaningful, sensible warp functions. We have two classes here. One looks like a Gaussian bell-shaped curve. The other looks like a sinusoidal pattern. Both have been perturbed by convolutional noise. So there is temporal misalignment introduced. And then when you pass it through this rate invariant autoencoder, and you visualize only the rate invariant component that you get from the latent blocks, and then you decode them, you get these functions which look like the rate invariant versions of what you sent in. So this is very remarkable for us, which means that we are able to create learned representations which have some level of invariance built in upfront. We are hoping that these things will have great impact in the field of wearables-based whatever, classification problem, regression problem, other kinds of analytics problems. I'm nearing the end, but I wanted to also very briefly mention a set of things that we've been looking at, which may also be on the horizon as far as the methodologies are concerned, geometric methodologies. It turns out, I may not have the time to go through in great detail, but here is a very quick example. I work very closely with researchers who build real-time interactive biofeedback methods for human movement so that you can, if you suffer from a neurological condition like stroke or other kinds of conditions which lead to motor deficit, one of the therapy protocols is to provide you feedback of your movement strategy. So the neural pathways which have been damaged, because of which you have motor control issues, can be rewired through other sense augmentation methods, for instance, sound, haptics, visual feedback, etc. One of the critical components in these applications is to take human movement and try and measure its deviation from some kind of an optimal path and use that deviation signal, that error signal, to drive feedback like sound. So here is what it may sound like. What you will see is a person with these marker sets for motion capture, try and reach for an object on the table. And you will see that as they you sort of expect the trajectory to be somewhat straight line, but sort of curved like parabolic. The more it deviates from that idealized trajectory, the more the sound goes off. So let's hear real quick. All right, good. So what you're hearing is a set of tones spaced out in time according to certain meters, right? And the speed of the hand, there are results in biomechanics that say for a reaching activity, the speed of the hand should follow a bell-shaped profile. So as you're moving forward with peak speed, the gap between the notes can be modulated based off of that. So you can convert interesting, you can control interesting parameters of the sound or other means of biofeedback through features of the movement in real time like this. But what features to use for biofeedback is an open question. There are some easy answers, like let's use the speed of the limb, or let's use the deviation of the pathway from some assumed notion of optimal or normal trajectories, which are all reasonable answers. These things, however, don't scale well if you're looking at multi-joint movements, these things work well. For single joint movements where you can look at trajectories in space and then measure errors and you use that intuitively. If I had to say the same thing for full body movements or even full limb movements with 3 or 4 interacting joints, what is optimal in the space of 3-dimensional joints is not very clear, but there are some approaches which I believe will be fruitful in the future. Without being super precise, all I wanted to say was one way to think about multi-joint human movement, assuming, let's say, you have joint angles. So this is special for motion capture where you have stick figures available to you, or you have some other means of estimating angles between joints. You can think of multi-joint human movement as a trajectory on a product of tori, right? Each angle can become a part of a circle. So 2 joint movements can become points on a tori, and more joints can become, can be represented also as multi-dimensional tori. What we find, and there is some evidence for this also in other people's work in biomechanics. We were motivated also by work from the Rehab Institute of Chicago by Ferdinando Mussaivaldi, who found that under certain carefully constructed experiments, under this way of thinking of multi-joint movement as points on tori or trajectories on tori, under appropriate feedback, and they were looking at visual feedback, we looked at sonic feedback. In both cases, we find that under appropriate biofeedback, movements tend to converge to geodesics on the tori. Now, some of these things are not very precisely done yet by us. These are some initial empirical findings. And we are looking at ways to actually testing these out with our partners in Virginia Tech, Thanasis Drakakis. But these are very exciting results for me, because this is an answer to a very important question for multi-joint biofeedback, which is how do you represent multi-joint movements in a compact way so that one error signal that you can derive from it can drive complex feedback. And my initial answer is some notion of closeness to a geodesic, some notion of it can be clearly simple things like, you know, projections onto a geodesic, or it can mean things like looking at the norm of the covariant derivative. If it's close to a geodesic, maybe the covariant derivative should be close to 0, but that's not how things work in real cases. I mean, geodesics are constant speed curves. Human movement is never constant speed. There is always, you start from 0 speed, you end at 0 speed, and there is a bump somewhere in the middle. So it aligns to a geodesic curve, but it's not necessarily it's a geodesic. So I'm looking at interesting new ideas to bridge these gaps, and I'm hoping these are fruitful areas for future inquiry. So thank you so much. I thank you for listening, and I'll be happy to take questions. Generally speaking, the conclusions are there is an interesting space here in movement-based health for rehab, for biomarkers, for general health and well-being applications, where there is need for new mathematics of many different kinds, both for representing movement in trivial ways, and also creating inferences that are robust, that are invariant to certain well-understood sources of variation. With that, I thank you again, and happy to take questions. Feel free to email me if you see this talk. Thank you so much.